Hi everyone. Let's look at our next lesson, lesson 2.2, which is finding the payment value, or N, our total number of payment periods. So our last lesson, we looked at the future value and the present value of an annuity. Okay, we looked at examples starting with future value and then moving to some present value situations. But what if you want to know, you don't know what your payment will be, or you don't know your total number of periods? So you can rearrange this formula to solve for those. And they're very useful in situations like a mortgage, right? You know the present value when you purchase your home, okay, if you purchase it for $200,000, okay? And normally the bank will give you an interest rate, and you can pick a number of years, typically if you're in mortgage. A lot of people will pick 25, all right? And using that data, they can calculate what your payments will be depending on your payment frequency, right? Bi-weekly, monthly, items like that. Okay, so this item, you'll see it used practically in a lot of cases, and in every instance they use calculators. All right, so you can go to a website and see mortgage calculators, for example, when you're buying a house. So just like our last lesson, I'm going to give you the formulas to find payment. Okay, in this instance, it depends whether you know the future value or you know the present value. And these are just simply the future value and present value formulas for annuities that we learned in our past lesson, rearrange. So if you know the future value, your payment, you can calculate it by taking your future value multiplied by your periodic interest rate, divided by this term you're becoming familiar with, 1 plus the periodic interest rate to the exponent n. Again, n is the total number of payment periods, minus 1. On the flip side, if you know the present value, the formula looks a little bit different. Again, remember, the present value formula looked a little different, having this 1 divided by 1 plus I term at the bottom. So if you know the present value, it's simply the present value multiplied by the periodic interest rate, okay, divided by 1 minus, and then a right term, 1 divided by 1 plus the periodic interest rate to the exponent n. And again, n is the total number of payment periods. Okay? So let's apply it. First, looking at a future value formula. So what deposit made at the end of each quarter will accumulate to $10,000 in 4 years at 4% per annum interest compounded quarterly? Okay? Keep in mind a couple items to notice here. It's again at the end of each quarter, okay? And your deposits are made quarterly and your interest is quarterly. So this is an ordinary simple annuity. This is important for you to understand these distinctions. So, like I said, it's accumulating to $10,000, meaning $10,000 is the future value. So that means we know the future value, so we can use our payment formula knowing future value. So your payment is equal to your future value times your periodic interest rate divided by 1 plus the periodic interest rate, the exponent n minus 1. Okay? So your future value, in this case, is $10,000. That's how much you want it to be. Your nominal interest rate is 4%, which remember is 4 divided by 100, removing the percentage sign, which is 0.04. Your number of compounding periods per year, M, is 4 because it's given as quarterly. So your periodic interest rate, I, is equal to J divided by M, or 0.04 divided by 4, which gives you 0.01. Your last item, okay, is your number of payment periods, N. In this instance, it's 4 years, and it's quarterly, so you make 4 payments a year. So in total, you're going to make 16 payments towards this annuity. So substituting all of these values in, your payment is equal to your future value, $10,000, times your periodic interest rate, 0.01, divided by 1 plus 0.01 to the exponent 16 minus 1. Okay? So if you calculate this out, remember, doing the appropriate steps in these brackets is important. Remember back to order of operations. You get an answer of $579.45. So that would be how much you'd have to deposit at the end of each quarter to accumulate to $10,000. Okay? Let's look at one more example. If you want to have a $5,000 balance in your savings account in 3 years, how much must you deposit at the end of each month if interest is 4.5% compounded monthly? So again, end of each month, and it's compounded monthly. So again, an ordinary, simple annuity. And it's wanting you to have a $5,000 balance in 3 years, meaning that is the future value. So again, we start with our future value formula. Okay, so the payment with future value known is equal to your future value times your periodic interest rate divided by 1 plus your periodic interest rate to the exponent n, your total number of payment periods, minus 1. So in this instance, your future value, well, it says you want it to equal $5,000. Okay? You know that your nominal interest rate is 4.5, whoops, I wrote 45, 4.5%, which is 4.5 divided by 100, removing the percentage sign, which gives you 0.045. Okay? Your number of compounding periods per year, M, is 12 because it's given as monthly. So your periodic interest rate, I, is equal to J divided by M, which is 0.045 divided by 12. And if you do that, you get 0.00375. Okay, remember, some of you might get 3.75 times 10 to the negative 3. And what that means is when that's in scientific notation. So you start with your decimal place and you move it 1, 2, 3 to the left, filling it in with zeros. Okay, so you'll end up getting the same 0.00375. All right. Our last item we need, N, okay, our total number of payment periods. Well, we know it's 3 years, and we know we're paying monthly, so it's 12 payments a year. So we're making 36 payments total. So knowing all this information, we can again substitute it in. Our payment is equal to $5,000 times 0.00375, our periodic interest rate, divided by 1 plus 0.00375, our periodic interest rate, the exponent 36, minus 1. So again, placing these numbers in your calculator, our payment is $129.98. Okay, so about $130 a month. All right, these formulas, like you can see here in this example, because you have the formula, once you figure out the variables, the future value, the periodic interest rate, and the total number of payment periods, it becomes pretty straightforward to substitute those values into the formula and solve. So looking at another example, okay, let's look at the present value. So instead of having future value, let's look at present value. What payment should be made semi-annually at the end of each period to pay off a loan of $8,000 in 10 years if interest is 10% per annum compounded semi-annually? Okay, so first of all, it's noting that you have a loan of $8,000. That's going to be your present value, right? You receive the $8,000 immediately. Other things to notice, payments are at the end of each period, okay? And the payments are made semi-annually, and the interest is semi-annually, which means it's an ordinary, simple annuity. You're probably already getting really tired of me doing that each question, The reason is once we get into other types, you're going to need to be able to distinguish which type of annuity you have, right? Because the formulas will change slightly. Okay? So in this instance, we're doing present value. So going back to that page, you can go back to the page in the PDF file that I posted, and you can find the formula for the present value, for the payment, when you know the present value. So in that instance, the payment is equal to the present value times the periodic interest rate divided by 1 minus 1 divided by 1 plus your periodic interest rate to the exponent n. Okay, the same variables we need to find, it's just a different look to the formula. In this case, our present value is $8,000. Our nominal interest rate is 10%, which remember is 10 divided by 100, removing the percentage sign, or 0.10. Our number of compounding periods per year in this instance, M, is 2 because it's given as semi-annually. So our periodic interest rate, I, is equal to J divided by M, which is 0.10 divided by 2, or 0.05. So the last item that we need is our total number of payment periods, N. So remember, it's saying 10 years in the question, and it's semi-annually, meaning 2 payments a year. So our total number of payments is 20. So now we have all of our information, we just have to substitute it into our formula. So our payment is equal to our present value, which is $8,000 for this loan, times our periodic interest rate, 0.05, divided by 1 minus 1 divided by 1 plus 0.05, and that's the exponent 20, right? Because the total number of payments is 20. Again, you place that in your calculator, and your payment will come out as $641.94. So as you can see, once you determine what type of annuity is, it's ordinary simple annuity, what data you have, your present value, your future value, and what you're trying to find, in this case, the payment. That is the majority of the problem, the majority of what you need to do in this question. After that, it's following the same steps we've been following in last unit and this unit to find your interest rates, your number of payment periods in this case, and substituting them into these formulas. So let's look at another example. Frank bought a new car valued at $9,500. He paid $2,000 down and financed the remaining amount over 5 years at 9% per annum compounded monthly. How much must, I wrote Derek here, I don't know who Derek is, but how much must Derek pay at the end of the month? That should obviously say Frank. So I'm just going to change it to Frank now. But what you're noticing, okay, is that Frank bought a new car for $9,500. Okay, so that means that's his present value, how much he purchased it for, but he paid $2,000 of that down, right? So that means he doesn't have to finance all of it. He's only financing the difference, okay? But one thing we do know is this is a present value, and you're trying to find the payment. So you can start with your payment is equal to your present value times your periodic interest rate divided by 1 minus 1 divided by 1 plus your periodic interest rate to the exponent n. Okay? So you know it's present value because you bought this car in today's dollars. Okay? And what it's asking for at the end is what he has to pay at the end of each month. Okay? The other thing you'll notice is the end of each month, it's compounded monthly, and he's paying monthly, which makes this, again, an ordinary simple annuity. Okay? That's why we could use this formula here to find the payment value. So the first item is what's his present value? His present value isn't $9,500 for this loan, right? He's only financing a portion of it. He's financing $9,500 minus what he paid on it. So his loan the present value of his loan is only $7,500, right? Because he already paid this $2,000 down and financed the rest. So $9,500 shouldn't be what your loan payments are based off of, right? It should be based off only the money you're borrowing. So we know our present value. Our nominal interest rate is 9%, which again is 9 divided by 100, removing the percentage sign, which is 0.09. In this instance, we're compounding monthly, so m is 12. So our periodic interest rate, I, is equal to j divided by m, or 0.09 divided by 12, which gives you 0.0075. Or, like I said before, you might see 7.5 times 10 to the negative 3. Again, you take your decimal, 1, 2, 3. So that moves the decimal and you place zeros there. You move the decimal corresponding to the number over here. In this instance, it was negative 3. So both give you the same answer. Okay. Lastly, n. Okay, so we know that he financed it. I'll move this so you can see it over a period of 5 years. And he does monthly payments. So he's making a total of 60 payments, 5 times 12, because 12 payments a year times 5 years. So now substituting these numbers into the formula, his payment is equal to the present value, 7,500, times 0.0075, the periodic interest rate, divided by 1 minus 1 divided by 1 plus 0.0075, the periodic interest rate again, all to the exponent 60. Okay? And if you calculate that out, you get a payment of $155.69. So that's how much Frank would have to pay monthly in order to pay down the remainder of his car loan. Let's look at one more example, this one with a little bit more in depth. Ben wants to retire in 25 years. He intends to deposit $1,500 at the end of each year for the next 25 years into a savings account. Once retired, he plans to make one annual withdrawal for each of the next 20 years. If interest is 6.5% per annum compounded annually, what is the amount of each of the withdrawal payments? So there's 2 steps in this problem, okay? The first step is before he retires. So this is year 0. This is 25 years into the future. He has payments of $1,500 each year for 25 years. So what you're going to find is we need to find the future value of the annuity at year 25. Okay, then he's going to make one annual withdrawal each year for 20 years. So at this point, that future value calculation, that becomes the present value to figure out what the payment would be for his annuity for the next 20 years. So our first step, okay, is to find the future value. So reading this question, payments are at the end of each year, okay, and his withdrawals are also at the end of the year, so they're also yearly. Interest is annually, which means yearly, so this can be treated again as an ordinary simple annuity. So that means your future value calculation is equal to your payment times 1 plus your periodic interest rate, that's to the exponent n, your total number of payment periods, minus 1 divided by your periodic interest rate. Okay, so this is just to figure out how much his annuity is worth at year 25. So what we know is we know his payments are $1,500. His nominal interest rate is 6.5%, which is equal to 6.5 divided by 100, removing the percentage sign, or 0.065. In this case, his number of compounding periods per year is 1, right? Because it's annually. So his periodic interest rate is equal to J divided by M, just 0.065 divided by 1, or just 0.065. Last item you need is N, okay, total number of payment periods. And this is over 25 years, and it's 1 payment a year. So 25 payments total. So you substituting these values in, your future value is equal to 1,500 times 1 plus 0.065 to the exponent 25 minus 1 divided by 0.065. Calculating this out, you get a future value of $88,331.52. So what that means is at year 25, Ben has $88,331.52 in this annuity or this account. And now he wants to use that money to take regular payments out. Okay, so that means that if we're starting at year 25 and we know this value, that is our present value for determining what our payments are. So on our second step, we know we're finding our payments. So our payment, knowing the present value, is equal to the present value times the periodic interest rate divided by 1 minus 1 over 1 plus the periodic interest rate to the exponent n, total number of payment periods. Again, this, I expect you, when we have a test, that you can have a formula sheet that I'll provide with these. You just have to start going through these problems and figuring out where each of these formulas kind of fits in. Okay? So, what do we know in this problem? We know our present value. I've got $88,331.52. That's in this account. Our periodic interest rate hasn't changed, right? It's still annually and it's still 6.5%. So we can keep 0.065. Our value for N has changed though, right? Because in this instance, I'm doing withdrawals for 20 years and it's annual, so 1 withdrawal a year. So that gives us a value of N of 20. So now, for the second part, we can just substitute these values in. So our payment is equal to $88,331.52 times our periodic interest rate, 0.065, divided by 1 minus 1 divided by 1 plus our periodic interest rate, 0.065, and that's the exponent 20. Okay, and if you calculate that out, you get a payment of $8,016.65. Okay, so that is how much he can take out as a withdrawal over the next 20 years. All right. So the second half of this lesson is, instead of looking at for the payment, we're going to look at finding our total number of payment periods. Okay. And if you remember back to our first unit, our good old friend ln is back, that ln button on your calculator. And you're going to need to use that button in order to solve for n. Again, remember, it's because the term 1 plus I, or the periodic interest rate to the exponent n, in order to be able to solve for that n, you had to take the ln of both sides. All right. Again, I'm not going to go over how these formulas were derived. All right. I do expect you to know how to apply them. Just like in the past, okay, when we looked at payment, it depends on what you know. If you know the future value, then this is your formula. N is equal to, it looks like a very complicated formula, but as long as you take your time and take your, put the steps in order in your calculator, you'll get the right answer, okay? So it's equal to the ln, and then within the ln brackets, it's the future value times the periodic interest rate divided by what your payment is, plus 1. Okay, so this entire term, you calculate it, and then you take the ln of that, right, using the ln button on your calculator. And that's divided by the ln of 1 plus the periodic interest rate. Okay? On the flip side, if you know the present value, then your total number of payment periods is equal to the ln of everything in this bracket, 1 minus the present value times the periodic interest rate divided by your payment, and that's divided by the negative ln of 1 plus I. So what the negative ln means, remember, negative ln of 1 plus I, that's the same as negative 1 times ln 1 plus I, right? That's what that negative means that's sitting behind the ln symbol. All right, that's very important because when you're doing these calculations, what you'll notice, there's a reasoning behind it that I won't get into, is that when you take the ln of your numerator, you're always going to get a negative number. Okay, it's a function of this formula. It's a function of the fact that you have 1 minus a certain number within your brackets. So you also are dividing by a negative number here, so that when you come out, your final solution will have a value for n that is positive. And that's important, right? You can't have a negative number of payment periods, right? It has to be a positive number. So I won't go into all the details as to why that's the case, but it's very important that you input this in the form into your calculator correctly. So let's look at an example. And this example is for future value. How long will it take for $200 deposited at the end of each quarter to amount to $5,726.70 if interest is 6% per annum compounded quarterly? Okay, so a couple things to notice. One, it's this to amount to a certain value. That means it's the future value. And you'll also notice the payments are at the end of each quarter and it's compounded quarterly. So again, it's an ordinary, simple annuity. Okay? So starting with your formula, again, it's nice to have these formulas sitting with you when you're looking at these questions. N is equal to the ln, okay? And that's of the future value times your periodic interest rate divided by what your payment is, plus 1, all divided by the ln of 1 plus your periodic interest rate. So what do we know in this question? We know that our future value is $5,726.70. That's provided in the question. Our payment is $200. That's how much we're putting down. We're putting in at the end of each quarter. We also know that our nominal interest rate is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. Our number of compounding periods per year, M, is 4 because it's given in the question as quarterly. So our periodic interest rate, I, which is J divided by M, is 0.06 divided by 4, or 0.015. Now the last item we obviously don't know is N, but we know everything else that we can now substitute into this equation. So N is equal to the ln of the future value, $5,726.70, times the periodic interest rate, 0.015, divided by our payments, 200, plus 1, and that is all divided by the ln of 1 plus 0.015. Okay? So let's look at an example. How long will it take for $200 deposited at the end of each quarter to amount to $5,726.70 if interest is 6% per annum compounded quarterly? So a couple things we notice here, that the end of each quarter and interest is also quarterly. So it's an ordinary, simple annuity. All right? Other thing to notice is we're trying to find how many periods it'll take to amount to this value, which means we're trying to find a future value, okay? Or we're using a future value, all right? So that means the formula for n using future value would be used. So n is equal to the ln of the future value times the periodic interest rate divided by your payments plus 1 divided by the ln of 1 plus the periodic interest rate. So what we know in this problem, the future value is equal to $5,726.70. Our payment is $200 each quarter, and our nominal interest rate is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. So our last item, m, we know it's quarterly, so that means m is 4. So our periodic interest rate, which is j divided by m, is equal to 0.06 divided by 4, or 0.015. Our last item, we know n is equal to the number of years multiplied by the number of compounding periods per year. Okay, we don't know the value of n yet though, okay, in order to figure out the number of years. So let's solve for n first, okay, using our formula. N is equal to the ln of our future value, $5,726.70, times our periodic interest rate, 0.015, divided by our payment, 200, plus 1. That's all divided by the ln of 1 plus 0.015. Okay, so I'm going to show you this in a couple steps. So n should be equal to the ln. If you calculate everything else out in this numerator, you get ln of 1.4295. And in the denominator, you should receive the ln of 1.015. Okay? So that will give you an answer. Okay, the ln of 1.4295 is 0.357326. Again, I rounded it. Divided by 0.014889. Okay? If you calculate that out and round it, you get a number of payment periods of 24. Now keep in mind, that's the number of payment periods. It's not the number of years. Okay? Because remember, n is equal to the number of years times the number of compounding periods per year. So that means that n is 24, and it's equal to the number of years multiplied by the number of compounding periods per year. In this instance, it was quarterly, so it's 4. So to solve for number of years, you need to remove the 4 from the right-hand side. So you divide both sides by 4. On the right side, the 4's cancel. So you're left with the number of years is equal to 24 divided by 4, or 6. So it'll take you 6 years to amount to $5,726.70. So remember, when you're finding n, just like we did in the first unit, there's an extra step involved if you're trying to figure out if it's the number of years. Okay? So let's look at another example. How many payments will it take for your bank account to grow to $3,000 if you deposit $150 at the end of each month and interest is 9% per annum compounded monthly? Okay? So keep in mind, it's asking for how many payments. It's not asking for the payment value, because that's provided in the question. It's asking for how many payments, right? Because remember, n is the total number of payment periods. Or in other words, the number of payments that you've made over the course of this investment or payback if it's debt. All right? So first thing to keep in mind, you're depositing at the end of the month. So monthly, monthly, and the end of the month. So this is an ordinary simple annuity. okay? And we're trying to get it to grow to $3,000, meaning it's a future value. So you have to use the formula for n that involves future value. So remember, n is equal to the ln of the future value times the periodic interest rate divided by your payments plus 1 divided by the ln of 1 plus the periodic interest rate. So what do we know? We know in the question the future value you want it to be is $3,000, and we know our payments are $150. Our nominal interest rate, J, is 9%, which is 9 divided by 100, removing the percentage sign, or 0.09. And we're given in the question that deposits and compounding periods are monthly, so M is equal to 12. So our periodic interest rate, I, is equal to J divided by M, which is 0.09 divided by 12, which will give you 0.0075. All right, so now that we have all this information, let's substitute it in to find the total number of payment periods, N. So N is equal to the ln of the future value, 3,000, times 0.0075 divided by 150 plus 1 divided by the ln of 1 plus 0.0075. So again, doing this in steps, n comes out to the ln of 1.15. Okay, that's if you do everything in brackets and properly on your calculator, divided by the ln of 1.0075. Okay, so if you calculate that out, you'll get a number of 18.7, meaning that you have to do approximately 19 payments. You can't have part of a payment. So 19 payments for your account to grow to $3,000. Okay? Now, let's use the other version of that formula, and let's try and find the present value. So how many quarterly payments of $600 are required to repay a loan of $5,400 at 6% per annum interest compounded quarterly? Okay? So we're repaying a loan. Okay? So loans are present values, right? Because you've obtained that money today. And you're trying to figure out how many of these payments have to be completed. Well, again, quarterly and quarterly. I didn't write it in here that it was the end of the month, but this is an ordinary, simple annuity. Okay, so going back a couple slides for our formula, we know its present value. So N is equal to the ln of 1 minus the present value times the periodic interest rate divided by the payment. And that's divided by, remember, the negative ln of 1 plus the periodic interest rate. Okay? So what do we know in this question? Well, we know our present value is $5,400. That's how much our loan is worth. And we know our payment is $600. We also know that our nominal interest rate, J, is 6%, which is 6 divided by 100, removing the percentage sign, which is 0.06. In this instance, we're given that it's quarterly, so our number of compounding periods per year is 4. So our periodic interest rate, I, is J divided by M, or 0.06 divided by 4, which gives us 0.015. Okay, substituting these values in, N is equal to the ln of 1 minus our present value, $5,400, times 0.015, our periodic interest rate, divided by our payments, $600. Okay. That's divided by the negative ln of 1 plus 0.015. So if you have placed these in your calculators correctly, you'll get that n is equal to the ln of 0.865 divided by the negative ln of 1.015. So that is actually equal to negative 0.145 divided by the negative of ln 1.015, which is negative 0.01489. So if you calculate that out, you actually get, okay, a value of 9.74, which would round to 10. Okay, you're always going to round these up, meaning you have to do an additional payment so that it will account for the additional payment. You can't have a partial payment, right? And if you round down, it means you'll be a little bit short on paying back the loan. If you round up, then it's an additional quarter to have it paid back. Okay, so that means it's 10 quarters. Okay, remember that's what n is. It's a number of periods, right? Which in other words, we've got 10 quarters here, which if you wanted to convert that to years would be 2.5 years. So our last example, all right, Art received an $8,000 bonus. He invested the money in an annuity that provides semi-annual payments of $1,200 at the end of every 6 months. Interest is 6.25% per annum compounded semi-annually. How many payments will Art receive before the money runs out? So we know that we've got a present value. He got this really nice bonus of $8,000 and decided to invest it. Okay, so first thing I've noticed is his payments are coming at the end, and they're coming semi-annually every 6 months, and our interest is also semi-annually. So this again is an ordinary simple annuity. Okay, and we know that we're given the present value. Okay, so we're looking at how many payments is he going to receive. So what's the value of n? So n, because it's present value, is equal to the ln of 1 minus the present value times the periodic interest rate divided by our payment. And that is divided by the negative ln of 1 plus our periodic interest rate. So our present value is the amount he got for his bonus, $8,000, and his payments are $1,200 because that's how much he's planning to take out. In this instance, nominal interest rate is 6.25%, which is equal to 6.25 divided by 100, removing the percentage sign, or 0.0625. Okay? It's given that it's semi-annual, so our value for m, our number of compounding periods per year, is 2. So our periodic interest rate, I, which is j divided by m, is 0.0625 divided by 2, which gives us 0.03125. Okay, just placing that in your calculator. So, substituting all of these values in, n is equal to the ln of 1 minus our present value, 8,000, times 0.03125, our periodic interest rate, divided by our payment, $1,200, and that's divided by the negative ln of 1 plus our periodic interest rate, 0.03125. Okay? Again, if you place these numbers in your calculator correctly, you'll get n is equal to the ln, okay, of 0.7917 divided by the negative ln of 1.03125. Okay? If you place those in your calculator, you get negative 0.2336 divided by negative 0.03077. Remember, the negative on the denominator comes from the fact that this is the negative ln. Okay? You calculate that out, you get 7.6, or in other words, again, rounding up, Art would get about 8 payments before the money runs out. Okay? So this was all for this lesson. Okay, it's a little bit shorter than our previous lesson. Again, there's a lot of formulas, a lot of steps. I encourage you to watch these more than once. Try the question before you look at it. If you want to, you can just hit pause on the video, try the question. The answers are provided in the bottom left corner. And then hit play if you want to watch any steps that I do. I do encourage you to not look at the answer before you try the problem. Then sometimes what ends up happening is you work towards that answer as opposed to just working through the problem. But as like any lecture, if you have questions, send me an email. It's the easiest way to try and get a hold of me. Or make sure you bring your questions to our tutorial sessions, okay, on Thursdays. Those are there specifically just to help you kind of move along. I'll try my best to answer questions. I schedule those for an hour, but if they do go longer, again, that's entirely okay. So thanks, everybody.